If you work with large language models, you know the pain point, the context window. It always feels like the final bottleneck. You've got terabytes of data, maybe gigabytes of code, but your LLM can only see a tiny fraction of it at a time.
Right. But what if the model could literally program its way out of that box?
And that is the core idea behind this paper we're looking at today. It's called Recursive Language Models, or RLMs.
That's right. Paper 2512.24601V1 by Zhang, Kraska, and Kitab. And they propose this really general inference strategy that just stops treating the long input prompt as this static sequence of tokens.
Instead, it treats that massive input, we're talking 1 million, 5 million, even 10 million tokens, as a dynamic object, an object that lives in an external Python read-evil-print loop, a REPL environment.
And the mechanism is both really clever and surprisingly simple. The LLM writes and executes code in this environment to look at the prompt, to programmatically break it down, and this is the key part, recursively call itself, a sub-LM on these tiny relevant snippets.
The results of this shift are they're game-changing. RLMs can successfully handle inputs that are up to 2 orders of magnitude beyond the model's actual context window. We're talking scaling up to 10 million tokens and probably beyond.
And this isn't just about making the window bigger. It's about unlocking totally new capabilities. On a really complex task, oolong pairs, which needs to find pairs of data across the entire context.
Which is a nightmare task.
A total nightmare. RLM with GPT-5 got an F1 score of 58%. The base model, it got 0.04%.
0.04. That's a complete failure. That's guessing. 58% is a working, functional system. That's a transformation. And they're saying this is done at a comparable, sometimes even cheaper average cost per query.
Exactly. Okay, so let's really break this down and figure out how this REPL trick is redefining context limits for these huge, long horizon tasks.
Let's do it. I think we have to start with just how bad the problem is that they're trying to solve. The industry is pushing LLMs on these long horizon tasks, right? Analyzing deep research, complex legal filings, entire code bases.
Huge contexts. Tens of millions of tokens.
And the standard context windows just can't keep up. It's not even an option.
And it's not just about hitting that hard token limit. There's this phenomenon of context rot, which Hong and others observed. Even within the supposed limits of a model like GPT-5, the quality just degrades as the context gets longer.
Oh, we've all felt that. You push too much into the prompt, hoping it remembers the first thing you told it when it's reading item 100,000. And you can just feel that information decaying away. That's exactly the problem.
Right, and the paper's first figure really makes this clear. Degradation is a function of both input length and, crucially, task complexity. If you look at a simple task, like SNIAH, that's a single needle in a haystack search, the processing cost is pretty much constant. The base LLM handles that, reasonably well.
But the second you add complexity, it all just falls apart.
Completely. Look at the quadratic complexity tasks, like oolong pairs. That requires aggregating info over pairs of entries scattered all over the input. The processing cost scales as ON squared, relative to the input length n.
ON squared. The classic complexity killer. So if you double the context, you quadruple the workload on the model trying to match up those data points.
Exactly. So it's no wonder the base LLM's performance just catastrophically collapses at much shorter context lengths for these dense, complex problems.
And this is why the old tricks don't work. We've all tried things like context condensation or summarization, right? You summarize the first part to make room for the next.
But that's built on a faulty assumption. It assumes that early details can be safely forgotten or compressed.
And for these complex tasks, that's just not true.
It's the failure mode. For multi-hop reasoning or that dense aggregation in oolong, you need fine-grained access to details scattered across the entire massive prompt. If you summarize, you're literally deleting the evidence you need.
Which brings us to the core architectural breakthrough of RLMs. They just flip the script entirely. The key insight is, why are we trying to cram this 10 million token prompt directly into the transformer's tiny context window?
Right. Instead, the prompt, let's call it P, is loaded as the value of a variable named context inside a standard Python REPL environment. This REPL is basically the LLM's external memory and its toolkit.
So the LLM's job is no longer to generate a direct text answer. Its primary job is to output executable Python code that runs in that REPL.
Precisely. This means the LLM can now interact with the long prompt symbolically. You can write code to peek into it, to decompose that massive string P. Maybe it runs a reject search for a keyword, or it just prints out a specific 500 token chunk.
And it sees the results of that code. It's like it's a programmer debugging a huge file. And the most critical piece here is the recursion. The code the LM writes can actually construct a subtask and then invoke query. It recursively calls a sub-LM on a smaller, relevant chunk of that huge context variable.
And that's the architectural difference that gives it so much power. Previous methods, they focused on breaking down the task, the question. But the prompt they were reading was still stuck inside the physical context window.
But here, the prompt is virtually infinite. The RLM lets the input context itself scale way beyond the model's physical capacity because the REPL is handling the storage. The LLM only ever sees these small, filtered chunks it asks for.
So let's talk about the performance. The evaluation used top-tier models,
Yes.
right? GPT-5 and the open-source Qwen3-Coder model.
And they compared RLMs against just calling the base LLM directly, Kodak agents with retrieval, and these iterative summary agents.
And they structure the tasks perfectly to test how it scales. You've got constant cost, linear cost, and then that quadratic beast, oolong pairs. Plus, these massive multi-hop reasoning tasks like BrowseCom+, reasoning over up to 11 million tokens.
11 million.
Observation 1 is the headline finding. RLMs maintain strong performance way into that 10 million token range. On BrowseCom+, which was 6 to 11 million tokens, RLM with GPT-5 achieved 91.33% accuracy.
Wow. And how did the baselines do?
The next best was the summary agent, which scored 70.47%.
So a 20+ percentage point gain. That basically proves that summarizing just doesn't work. The RLM is finding crucial evidence that the summarizer deleted.
Exactly. And back to oolong pairs, this is where you see this emergent capability. The base models, again, F1 scores below 0.1%, total failure. The RLM's ability to programmatically manage that dense information gets it to that 58% F1 score.
That's the difference between a system that's broken and a system that you can actually deploy.
Absolutely.
Okay, but this is where it gets really interesting for me when you look at the ablations. They tested RLM without the recursive subcalling part, so this tells you what the REPL environment is doing on its own.
Right. And observation 2 showed that the REPL environment by itself is powerful. It lets the model scale beyond the context limit, and it outperforms the base models on some tasks just by using it for storage. But for those really information-dense tasks like oolong, that ability to programmatically create subtasks and make recursive calls is vital. It's the secret sauce.
So the REPL gives you the ability to scale the input size, but the recursion gives you the reasoning power to actually make sense of that massive scale.
You've got it. RLM with recursion outperformed the version without it by anywhere from 10 to almost 60% on those hard, dense tasks.
Okay, let's talk cost. That's always the first question. Recursively calling an API sounds expensive.
You'd think so. But observation 4 is that the median inference cost for RLMs is actually comparable to a single base model call. Sometimes with GPT-5, it was even cheaper than the median base run.
Wait, hold on. How is that possible? How can making more API calls be cheaper?
It's all about intelligent filtration. Think about it. The RLM was up to 3 times cheaper than a summarization baseline because it selectively views only what it needs. It uses code to filter the context first instead of forcing the entire 10 million token input through the expensive attention mechanism every time.
I see. So it's doing targeted reads instead of one massive brute force read. But there's a catch, right? There has to be a catch.
There is, and it's a big one. High variance. Figure 3 shows these sharp spikes at the 95th percentile for cost. If the RLM gets stuck in a long loop searching, verifying, researching, the cost and the runtime can explode.
And that variability could be a total non-starter in a production system. You need predictable latency.
It's a critical limitation, and the researchers are upfront about it. The problem is made worse, because right now the calls are synchronous, they're blocking. The model has to wait for each subcall to finish before it can do the next thing.
Which seems like a solvable engineering problem, at least.
It is. But let's move to the emergent behavior, because this is where you can really see the new paradigm in action. By forcing the LLM to output code, it starts to act like a genuine system administrator.
How so?
Well, we saw examples of RLMs using code, like regex queries, to filter the input context based on its own priors. It narrows the search space before it even ingests the text.
So like RLM with GPT-5 searching a huge document set, and it just executes a search for the keyword festival or law union without having to read all the documents first.
Exactly. It's teaching the LLM how to write its own internal search queries against the prompt.
That's filtering before ingestion. That's a huge efficiency gain.
It is. And on tasks that needed really long outputs, like oolong pairs, the RLMs used the REPL variables to build the final answer piece by piece. They'd solve subproblems, store the results in variables.
And then stitch them together at the end. So the final answer doesn't have to be generated in one go, which avoids the output token limit.
Precisely. What's also fascinating is that while this RLM idea is model agnostic, it worked with both GPT-5 and Qwen3-Coder. Their behaviors were totally different.
Oh.
Qwen3-Coder was, let's say, overly liberal with its subcalls, sometimes making thousands of calls for a simple task that GPT-5 solved much more conservatively. It suggests a big difference in their internal planning abilities.
And those extra calls led to this bizarre failure mode you mentioned.
The most bizarre. We saw cases where Qwen3-Coder did all the hard work. It constructed the correct answer, stored it perfectly in a Python variable inside the REPL, and then at the very end, it just failed to return that variable.
Wait, what?
It chose instead to generate a new, completely incorrect answer as its final output.
So, hold on. The model did the hard part. It used programmatic logic, it found the data, it stored it safely in its own memory, and then at the last second, it just ignored its own work and hallucinated.
Exactly. It's fascinatingly dumb, right? It shows that while these models are getting great at complex planning and code generation, that final decision-making layer, understanding the return this value instruction, is still imperfect.
They're great programmers, but sometimes they forget the final print statement.
That's a great way to put it.
Mm-hmm.
And it points directly to the future work. The researchers note that they need to fix that high-cost variance, probably by implementing asynchronous subcalls. That's a key engineering fix.
And they only went to a recursion depth of 1, right?
Yeah, that's the low-hanging fruit. Deeper recursion could unlock even more complex, layered reasoning.
So wrapping this all up, what does this mean for us? It feels like RLMs offer this powerful general paradigm that reframes the long context problem. It's not a hard token limit anymore. It's a problem of programmatic context management.
Right. It shifts the burden from the brittle neural network to a robust symbolic programming environment.
But the long-term vision here isn't just about hacking existing models to work this way, though that's clearly effective. It's about explicitly training models to be decision makers as RLMs from the start.
And that would, in theory, optimize away these weird failure modes and inefficiencies we saw with Qwen3.
This feels like it goes beyond just making context windows bigger. The RLM trajectories we see, the filtering, the planning, the self-querying, that looks like an explicit, visible, and maybe even a trainable form of reasoning.
It really does.
And that's the huge question this leaves us with. If we explicitly train LMs for this kind of recursive programmatic workflow, are we unlocking a totally new axis of scale, one that fundamentally redefines what context and reasoning even mean for the next generation of models? Could this be the path to making them not just bigger, but actually reliable, deliberate planners? Something for you to mull over as you start experimenting with massive context.